Hello, everyone. My name is Alan Fogwell. I'm the Chief Operating Officer of PTAC, and I'll be your host for this morning's technology information session on emissions management. We have three amazing speakers with us today. We're going to be talking about different aspects of emissions management, going from monitoring to mitigation, which is where we're straddling these days, understanding more about the actual emissions side of things, and then creating solutions to mitigate those emissions in the upstream oil and gas sector. Normally, what we do with these panel technological innovation or information sessions, I should say, is each of the speakers will have 50 minutes to have a discussion about their particular area. And then at the end, we'll open it up to questions. You can put your questions in the chat function, and we'll read out the various questions. Or you can put it into the Q&A function as well. We get both, but we'll be monitoring both. If you've got a preference, that's fine. But if not, please put it in the Q&A. So we'll get going. I'll introduce the speakers high level when they are speaking. I'll just introduce them all right now, just so you know who we have speaking on this webinar. So we have our first speaker is Jean-Philippe Gagnon, who's the Field Applications Engineer for Telops. He's got a master's degree in physics and has worked at Telops since 2005. Our next speaker is Dominique Pichot. He's the product manager for Q Energy. He's a senior applications engineer at Q Energy. They're a leading manufacturer of Stirling engines, where he manages the compressed air pneumatics product line, and he's going to be speaking about that. And our final speaker is Idam Prabhu, who's the CEO and founder of Prabhu Energy Labs. He's an entrepreneur and inventor, and he spent a lifetime looking at energy innovation. And his focus today will be on an oxyparator device that he's developed for methane slip from lean burn engines. So with that, I'm going to ask Jean-Philippe. You'll start, and you can share your screen, Jean-Philippe, and proceed with your presentation.
All right. Thank you very much, Alan. Everybody should now see the screen.
Yes, we see it.
Perfect. Thank you very much. Thank you for PTAC for organizing this event here today and giving us the opportunity to talk about our technology, which is methane airborne detection solution. So I'll take you on a little tour of our tech, how it works, and what we're able to do with it. So I always like to start it off saying that these advanced screening methods to detect methane have been shown to work, and this is not coming from us, it's coming from the operators themselves, testifying to the EPA that these fugitive emissions can be reduced by using advanced screening methods. So I'll show you our technology here. So before doing that, just a quick word about Telops, who we are. So Telops has been founded in 2000. It's a Canadian-based company based out of, we're headquartered in Quebec City. So straight from the beginning, we started designing and manufacturing infrared cameras, and one of the first units we've designed is a hyperspectral camera. That was back in 2005, and we've continued building this camera up and make it better and better throughout the years. And we also developed a gas detection algorithm to go with this, to really take advantage of the information-rich data that streams out of this camera. And it started out from a ground-based perspective, but quite recently, or a couple of years back, we developed the airborne version of it. And now we offer a complete methane leak detection and quantification service. A little bit of history, again, back in 2005, where we developed our first unit mainly to detect harmful chemical gases for the military most of the time. But since then, we put it to work in various other contexts, such as environment, other industrial application as well. And you can see here our roadmap. So back in 2008, we had this big, bulky airborne sensor. We worked quite hard on reducing its weight, volume, and power requirements to make it fit into a very much smaller packaging. And that's the one that we run with now, called the HyperCam Airborne Mini. And future, we're still working very hard to shrink everything down to even smaller sizes. A unit that we call the Nano, which will be out in maybe next year. Sorry about the slides. My mouse is really responsive. Yeah, methane. So everybody knows methane's a powerful greenhouse gas agent with an atmospheric lifespan of around 12 years. So by working hard and detecting and minimizing emissions of methane, we can act on global warming potential and reduce its effect right in our lifetime, which is a real advantage here. Of course, we're not the only one in this business. There's optical gas imaging that's been around for quite some time here, helping out on localizing emissions, but they are limited in the fact that they cannot differentiate the type of gas. Of course, if you know it's methane, fine, but if you don't know, like this camera won't tell you. And of course, it gets really expensive if you're trying to map a complete asset or miles and miles, hundreds or thousands of miles of pipelines with simply by walking along it with a OGI camera. So the next thing up is aerial surveys, and this is where we fit in. So our tech is able to differentiate the methane from different other hydrocarbon emissions, and it's well adapted to map a large area and hundreds of or thousands of kilometers of pipeline. All right, there it is, our airborne HyperCam Mini. As you can see here, as I said at the beginning, it's quite a smaller package than what we're used to. So it comes in around the 30 centimeter unit. This one's a passive camera. So what I mean by passive is that it doesn't emit any light. It doesn't shine a laser beam and look at the reflection. It only collects whatever radiance or whatever infrared energy comes off the ground. So it works like a typical camera. So it's a snapshot type camera, but it does take a little bit of time to capture the image, just by the fact that after capturing the image, we have to decompose it into a multitude of wavelengths or wave number. So we decompose the light spectrum, just like a rainbow, just like a prism would do to a rainbow. So we look at the different infrared colors. And because methane has a very specific color associated with it, let's say the green spike is very intense. So by spreading out all the wave numbers or the wavelengths and looking at the green component, if we see a spike in the green in our measurement, then we know it's associated to methane and nothing else, because methane has a fingerprint in the infrared. Advantages, as I said, we can look at methane, but also any other compounds that have an infrared signature. This sensor can pick it up just with the same data. It doesn't have to refly or collect additional information. Everything is contained in the data set that we've collected. As the previous slide mentioned, it's quite flexible and adaptable. So we've been using it in Alberta, for example, aboard this Bell 206 helicopter. It fits right in the cargo bay, looking downwards, of course. In Europe, we've used it on the side of the aircraft for some really small manned aircraft, or larger twin engines aircraft. We can put the sensor in the belly of the aircraft. So very flexible multi-platform system. Being a passive infrared sensor, so what it actually measures the temperature difference, if you like, of the methane gas cloud as opposed to whatever object lies on behind it. So in this case, for our detection performance, there needs to be what we call a thermal contrast between the gas cloud, the methane gas cloud, and the background, which consists of the ground itself. So if we have this thermal contrast, then we can measure methane very accurately. And on the slide here, I've put down, I've noted our typical optimal flight conditions. Bear in mind that these conditions are just they're the optimal ones to detect the smallest quantity of methane that this instrument can detect. If we're after larger leaks, we can, for example, fly higher than 350 meters. We can fly faster, or we can fly in different weather conditions, such as higher wind day, for example, because wind does affect the detection performance of the sensor, just because it's sprays or dilutes the gas quite significantly. But this sensor can work over day, night, and also it can detect methane over water surfaces or even over snow, as I'll demonstrate in a few slides. Let me take you on or explain what our service consists of. So it's basically 3 simple steps: pre-flight, in-flight, and post-flight analysis. So for the flying Telops, we don't own here. We partner up with experienced geospatial survey companies. So we have 3 partners on board right now with us: LSI in Alberta, Canada, Skycam, which are based in California, and Bar Geospatial, which are based down in Texas and also in Alberta. So with these 3 partners, we cover the whole of North America. These are very experienced, so they know what to do. They will optimize your survey performance and ensure good collection data, and also in a short time and very efficient or cost-effective manner. So a few more words about the general overview of our service. So in the pre-flight, what we need from the client is their GIS information about whether it be pipeline or sites. So we take in the area that they want to survey, and our team, together with our partner, we will design the optimal flight plan, discuss the flight plan, the schedule and goals with our client, and handle all aspects of the flight and survey logistics. Then our partner will go out and execute the mission. So do the flying and report results to us at Telops, who will do the processing, report on a day-to-day basis. What's nice also about our sensor is that it will give you real-time information. So right from the aircraft, our partner can detect the very significant methane leaks and report that back to the ground if need be. So that's a very a nice feature of our system. Or I have a little information or a short video here explaining how our system works for pipeline tracking. So in green, we have the track that our client gave us. So that's the pipeline he wants to survey. And in red, those are the inspection corridor segments that we will design to follow the pipeline track quite accurately. And in blue, what you have there is the track of the aircraft. So the aircraft just tries to follow the pipeline track as accurately as it can. So of course, at some places it won't be able because there's a sharp turn and the aircraft can do that. But our sensor will always keep track of that pipeline itself. So over top of that, I put in the individual images that were collected with our HyperCam sensor. So you can see each one of those images is right on top of the green pipeline track with completely 100% overlap. So there's no spot on the ground that we've missed. What we deliver afterwards, so after our partner has executed the flight, the data comes back to Telops, we analyze everything, and we provide in 24 hours, a complete detailed in-flight inspection report. Complete image data set is provided 24 hours to flight, and a few days later, you get the complete report back with with a complete list of everything we have found, all the leaks that we have found during that survey. An interesting fact also is that our technology will give you the minimum detection limit for every image collected. So even though we don't detect any methane leak, at least by saying to you that the detection limit for this image or for this patch of ground was this level, then you're basically insured, because we have a high probability of detection. You're pretty much ensured that we didn't see anything above that limit. So that's an answer. Even though we don't detect anything, that's an answer worth having on its own. I'd like to conclude with just a few graphs of the most recent results that we've managed to get. So we did a few months or a few years back, high level or detailed semi-blind testing in summer conditions. And we just recently did a very shorter semi-blind test campaign during the winter. And those are the results that I would like to share with you. But before doing that, a quick word about detection limit. So I said a few words about that earlier, but the detection limit for our sensor depends on flight parameters. So the higher the AGL that we fly at, the speed of the aircraft, for example, instrument settings. Those are our internal parameters of the camera, and also environmental conditions such as thermal contrast, wind speed, and relative humidity. So what we did, because these are kind of hard to wrap your head around that, what we did to simplify things is we made this what do you call it? Like a detection limit tool that allows you to, once you know all your parameters, you can input those, and output will be your estimated detection limit as a function of thermal contrast. So this is a really nice tool that helps our partner determine which time of day and which day is best to fly to achieve the performance required by our client. On top of that, we can link that back because we calculate the detection limit on every single image collected. We can, just as the graph on the lower right side indicate, we can plot the detection limit as a function of time of the survey to really determine if indeed it was the right conditions, the conditions were right, or if not, we can quickly go back up and collect more data during a more optimal weather window. Probability of detection, as you see those, the two graphs here, the one on the left is for summer, or let's say summer in the loose term here. Summer means no snow covered coverage on the ground. And on the right-hand side is winter conditions where there's snow on the ground. So on the left-hand side, you see we ended up with a probability of detection. So these were all semi-blind test campaigns that we've done. So the probability of detection is 93% at a release rate that is close to the detection limit, which was 1 gram per second, so around 3.6 kilograms an hour. And the probability of detection even climbs closer to 100% or 98% if the detection limit is higher. On the right, you see similar performance during winter where there's snow on the ground. So detection limit, probability of detection 90% at leak rates of 1.2 grams per second, so roughly 3 or 4 kilograms an hour. So we see really similar performances for summer and winter conditions. So key takeaways here, before I leave you with the rest of the team here. So our system does allow you to pick up methane emissions over your sites in a cost-effective manner. It's multi-platform. You can use it in different types of aircraft and detects not only methane, but any other hydrocarbons that have an infrared signature. And the result that we managed to get so far are very good. So there you go. Thank you for your time. And yeah, if you have any questions, let me know.
Okay. Thanks, Jean-Philippe. I think we're going to hold questions till the end. I think one of the fascinating things about your technology is the winter capability, which is extremely important in places where we have winter for 6 months.
Exactly.
That would help if we knew what was going on in the winter time. And we'll get into the summer-winter contrast afterwards because I think that'll be important. So thank you very much.